All right, welcome students to your rainy day. It is spring 2023 and we had our second like rain day where school got canceled. But unfortunately for us, no rest for the weary. And I emailed you guys last night through Canvas announcements that you would be getting a video lecture on what we're supposed to cover today. So if you could all get out your notes, please. And I am curious. I did ask you guys, I believe, to complete a couple problems in Unit 6. And let me quickly screen share. So Unit 6, we ended with calorimetry problem. Okay, and you guys should have watched a AP problem walkthrough on calorimetry. I don't really feel the need to go through that today. We can go through that tomorrow when you hopefully return in person. And I do just want to remind you though that I am going to be doing a homework check tomorrow that you did complete the calorimetry problem because it was the last topic in Unit 6 and it's a very important equation. Q equals MCAT is what we say. Q equals mass times specific heat capacity times change in temperature for a respective substance. And it allows us to calculate the amount of heat gained or lost during a heat transfer between two objects of different temperatures. Okay. And it was a really important topic. And then what you guys were asked to do is after doing the AP problem last night, you were also asked to watch a reversible reaction / chemical equilibrium pre-lecture. Okay. And so today, if we were in class normally, we would pick up, go over those problems and move on as in normal fashion. However, due to the rains, we will address the Unit 6 problem in class tomorrow or whenever we return. And we are going to piggyback off of chemical equilibrium and progress in how do we predict how a reaction in equilibrium will respond when that equilibrium is disturbed due to a stress or change. And so that's what we're going to focus on today. So if you haven't already watched that AP problem walkthrough that was technically yesterday's homework, please make sure to do that. And please make sure to do those 2 practice problems I asked you to finish up in the notes in preparation for tomorrow's discussion. And then of course, if you haven't watched the pre-lecture, go ahead and do that. Honestly, you could totally also just read the notes that I've uploaded onto my website. And if they make sense, continue watching this video. All right, so for those of you that are completely caught up, that are tracking with me, let's go ahead and begin our lecture. And of course, tomorrow I will be moving on as if you did watch this lecture. So hopefully you're not too far behind. So how do we, now that we know that reactions are reversible and that reactions respond when a stress is applied that would cause them to shift or to change where their equilibrium is found, where their balance is found, we can address a really important principle known as Le Chatelier's principle. And Le Chatelier was a French scientist, okay? Or Le Chatelier, I don't know French, so however you're supposed to say it. And what Le Chatelier's principle or Chatelier's principle tells us is that when a system at equilibrium, okay, encounters or experiences a stress or change of some sort that disturbs the equilibrium. Okay, that disturbs the equilibrium. The reaction will shift, okay, in a way that restores a new position of equilibrium. Okay, the reaction will shift in a way that restores a new position of equilibrium. Okay, and another way we can say that is it responds to alleviate the stress. We're trying to alleviate the stress. So, for example, and we're going to switch back to my camera. I'm going to stop screen share for a second. Man, I hope I haven't done this back and forth in a while. Stop screen share. Okay, so that was a nice pause. What I have here is a little balance, and you can kind of think of the fulcrum as the equilibrium point in a reaction. And so if we have, let's say, little bears, okay, let's say we have a reaction where we have some amount of products and reactants that, okay, let's see if it balances out, that are in equilibrium, okay? And maybe I add a little one. Oh, too much. Maybe I add a couple of them. Let's see if I can get this in equilibrium. Okay, that's pretty much in equilibrium. Oh, gee willikers. Ah, I got this, guys. Hold on. I think I can do this. Almost. Too much. There we go. Now we're in equilibrium. That looks good. Okay, so we're in a balance. The rate of the forward reaction is equal to the rate of the reverse. So our amount of concentration of product and reactant are, or I guess product and reactant are constant, okay? They aren't necessarily equal to each other in terms of the amount, but they are staying constant because the rate, the kinetic speed of the forward versus the reverse reaction are staying similar, okay? Are staying, constant and consistent. So what happens though is, what if I add a stress? Like, let's say I'm adding more reactant. What happens? Well, initially, the immediate result is that my reaction is now my balance is way down by the extra reactants, by the extra bear, okay? Little plastic bear. So how is my reaction going to respond? And that's where Le Chatelier focuses on, is the response, not the initial effect, but the response of the reaction to get equilibrium back. What it will do is my reaction will simply add or create, more product. Okay, simply create more product in order, okay, to undo, goodness gracious, as you can tell, I practice with this a ton, in order to use up or undo the excess, okay, 1 second. I dropped a bear, the excess reactant, okay? So, sorry, these bears aren't a perfect analogy, but I'm just trying to give you a scale idea. So, same thing could be said for what we would call that is the reaction would shift to the product. If I add a ton of reactant that initially creates a way too much reactant present, the reaction will shift its equilibrium to restore it, because now it's been disturbed, it's off balance, in such a way that it brings back balance. So what are we going to do? We're going to alleviate the additional weight of reactant, the additional stress. And what's going to happen is we're going to simply make more product using up more of that reactant. Therefore, we're going to favor the forward direction. We're going to favor the production of product in order to alleviate the stress or use up that additional reactant that we've added. And so what we see is that our equilibrium is restored, okay? But what had to happen was that the forward reaction had to increase and the reverse reaction had to decrease to allow for that to occur, okay? So I really hope I didn't make that more confusing through the graphic. I tried my darndest, okay? So big idea is, if you can kind of imagine a scale, and as long as you remember that it's the response that we're focusing on in terms of any change, not the initial effect, it's the response of getting back to central neutrality, back to equilibrium, then you can predict very accurately Le Chatelier's principle in all contexts. So let's look at the various contexts, and let's switch back over to screencasting. Okay. And, oops, that's not what I wanted. I wanted notability. All right. So what are the various stresses that can occur? And then the way, according to Le Chatelier's principle, that the reaction will respond to those specific stresses. So the first most obvious one that I used in my very sketchy little example is what if we change the concentration of a reactant or product? So if you add reactant or product, what you will see is that the reaction will shift, just like in my example, to use up or remove the additional concentration. Okay. So the reaction will shift to use up or alleviate the additional concentration of whatever species. Okay. And then if you remove reactant or product, the reaction will shift not to use up, but to produce or to make. Okay. Well, the reaction will shift to make more. Okay. To alleviate these removal or lessening, to alleviate the removal of the concentration of whatever species. Okay. So, for example, let's say I have a reaction that I have A plus B and it goes to C. And if I were to add A, okay, and I'll actually color code this. If I were to add additional A, that is my stress. I added A concentration, okay? What my reaction would do is my reaction would shift toward product. It would speed up the forward reaction, okay, so that I would use up that additional A species and alleviate the extra stress, or on that little demo, the scale, the weight, the extra burden of more A, I would alleviate that and create simply more product, okay? Causing my forward reaction to speed up and my equilibrium to eventually be restored, okay? So we would say the reaction would shift toward the product. Now, what if, I'll make this a little smaller. What if instead of adding more A, what if I subtracted A as a comparison? Well, what would happen is my reaction would shift toward reactants, toward the reactant side, would shift toward the reverse, would shift toward reactant. Because what it wants to do is it wants to alleviate the stress of not having enough A. So again, if it's a reversible reaction, and I totally forgot to make this look reversible. Oh my goodness, I can't believe I did that. This does not work unless it's reversible. What would happen is that my reaction would, to alleviate the stress of lacking A, it would undo the making of product and favor the reverse direction. The rate of reverse reaction would speed up to produce more reactants and fill in that missing or the removal of A, that decrease in A. Okay. So that's kind of what would occur. That's what Le Chatelier's principle tells us with respect to change in concentration as a stress. All right. So before I talk about the other few ways that we can examine a response in stress, let me just get clear on some terminology because I've just kind of been using it and throwing it out there, but let's just get synced up on it before we move on. So an equilibrium system, when you see the AP refer to an equilibrium system, what it basically means is a reaction at equilibrium. Okay. An equilibrium system is a reaction at or in the process of becoming or obtaining equilibrium. A stress is anything that disturbs the equilibrium. oops, I don't know how to spell equilibrium apparently. Shift toward product is one way of saying that our reaction response, so it's a response of reaction toward making more product, or another way of saying it is increasing the rate of the forward direction, right? The rate of the forward reaction, rate of forward reaction. On the other hand, a shift toward reactant is a response of reaction toward producing more reactants concentration, okay? Or another way of putting it is increasing rate of the reverse, rate of reverse reaction, R little r. So little AP FRQ tip, when you write about equilibrium responses, please make sure you say the reaction does restore equilibrium, not tries to restore equilibrium. And I know I make that mistake in lecture. I'm sure I've already made it where I just kind of say, oh, it's trying to restore. Well, in the chemists and the AP College Board, they just want you to emphasize that it actually does, because it wouldn't do this without restoring. Like it's a guaranteed, if it responds, it's going to respond to the point that it restores it. So they prefer that you just say the reaction responds and does restore the equilibrium, not the reaction tries to. Okay. So that's just a little small AP FRQ tip that I got from an AP grader. All right. So for this sample problem, what we have here is we have some HI is added to the system below. So we have a change in concentration and we have the stress of additional, okay? We have the stress of additional product. In what direction will the reaction shift to restore equilibrium? When the equilibrium is restored, how will the concentration of each substance compare to its concentration before the HI was added? So first and foremost, what we see is that we're going to see with the addition of product, we're going to see that the reaction is going to want to alleviate the stress of additional product. So it's going to now favor the reverse or shift toward the reactants. So we're going to say A, it's going to shift toward reactants. And B, what will happen is we will see that we will have a increase in terms of an increase in reactant concentration as a result. Okay, sample problem 2. Some solid calcium hydroxide is in equilibrium with a saturated solution of its ion. Remember, saturated means max ion dissolution in solvent. Okay. And this is a solubility equilibrium, which we're going to actually talk about. Charlie's going to teach you on Friday. So it's going to be in a couple of days that we really dig into this concept. The rate of dissolving equals the rate of recrystallizing, or the rate of dissolving equals the rate of reverse solidification. Some OH is removed by adding some hydrochloric acid. So we're removing OH by having it react. So we're decreasing our concentration of OH minus because of subsequent reaction. Okay, because of partnered reaction. In what direction will the equilibrium shift? So the equilibrium will shift if we are removing product via this a subsequent or a following reaction that uses it. What we will see is our reaction will shift toward product, because it's going to be constantly trying to replace that OH minus being used up. And what we're going to see is that how do the concentrations of the calcium and hydroxide ion compare after the added acid? Well, what we'll see is that overall, while the reaction is going to be, well, this is an arguable actually answer. You could say that the overall the concentration of calcium 2 plus and ion and hydroxide ion. Okay. Compare, let's see what the question. How will the calcium ion and hydroxide ion concentration compared to their concentrations before the acid was added? Well, we would say that after the acid, we could say that there's a general decrease after acid because the acid is using up. All right. But I would actually favor, I think that's a weaker answer. I would actually favor that your calcium and OH increase. I think that's a better answer because reaction shifts to produce more product. All right. So I could see you seeing that two ways. I think the better way, the more favored way, would be to look at it from the Le Chatelier principle way, considering that is our theme. Okay. So we will have you do these practice problems on your own. So go ahead and pause me and try this out on your own. All right, so hopefully you pause me, and hopefully for the first one, you got that the reaction would shift toward product. All right. This is because if you add in FeNO3, that will be a source. Okay, this is going to be a source of more Fe3 plus, which means you are adding reactant, which means you're going to want to use up that reactant and therefore respond in such a way that you make more product to use it up, alleviate the stress of additional reactant. And then for 2, you should have gotten shift toward reactant. Because what would happen is if you were to add sodium biphosphate to the system, okay, and that sodium biphosphate reacts with Fe, what would happen is we're actually using up Fe3 plus. Therefore, we are decreasing the concentration. So another way of writing it is therefore we're decreasing the concentration of Fe3 plus. If we decrease the concentration of Fe3 plus due to that subsequent reaction, what's going to happen is the reaction is going to panic and want to try to fill up that gap in reactant iron and therefore shift to make more of it. Okay, so when we talk about equilibrium, all right, it's important to understand when we talk about the equilibrium position, what that actually means. Because every time your reaction shifts, it creates a new position or point or fulcrum, if you want to use the balance analogy, of where the reactant and product concentrations will remain constant, where at what point will the rate of the forward be technically equal to the rate of the reverse. Okay. And so what we have to say is that the equilibrium position describes the relative concentration of reactant versus relative concentration of product, okay, at equilibrium. And this equilibrium position is going to be represented by a constant numerical value known as the equilibrium constant. And it's indicating the point at which in the reaction, the point at which the rate of the forward is equal to the rate of the reverse, the point at which a balance has been occurred where your reactant and product concentration stay the same. And it's going to be represented by a value known as the KEQ that we will get into tomorrow. Okay. But overall, when we see and we describe Le Chatelier's principle, what we're also subsequently describing is not only just a response to a change by the reaction, but we're also actually describing an equilibrium shift. And I've been already kind of hinting at that, but here's the effective or final kind of terminology. So we say that the equilibrium position has shifted toward the product when we say the reaction has shifted toward the product. And by the way, that means that we could say, in terms of yield wise, that we have increased our percent yield. When our equilibrium shifts, when our reaction shifts to favor the product or the forward, we actually see an increase in percent yield of reaction. So notice, if we understand equilibrium shifts, we can actually control the amount of product that we're getting, which in lab really is valuable to us if we're trying to be an industry and we're trying to get out a certain amount of product in a certain amount of time. If we could just change the reaction a bit to favor one direction via external stresses, that's really handy. Ooh. On the other hand, when we say that the reaction has shifted toward the reactant side, we basically said that the equilibrium position, the state of relative reactant and product concentration has shifted to favor the reactants, leads to an actual decrease in yield. So what if we don't want a certain reaction to occur in a reversible process? Well, we could, again, exploit external factors to decrease that yield of the undesired relative products, okay? So go ahead and try out the sample problem below, and then we'll move on to the other areas of effect. Okay, so hopefully you tried out this problem and you should have gone that if we were to add iron chloride to the following reaction, what we would see is that adding iron chloride results in the addition of iron 3 plus, which is a reactant, which is going to cause, again, a shift toward the product. Okay, or what you could say is that the equilibrium position is now favored toward products and results in an increase in percent yield, right? If you want to just kind of use all that terminology. So now that we've addressed kind of our terminology introduced through our first stressor, which was concentration, let's go ahead and address other factors that can stress. So what if we were to add surface area or add a catalyst to a reaction? For a heterogeneous reaction where we have a solid and a liquid, or like different states of matter, okay, for a heterogeneous reaction, we would actually see that no shift occurs. So an increase in surface area actually has no effect on equilibrium. And here's why, okay? It's because both the rate of the forward and reverse would speed up. Collision would be increased in both directions. Both the rate of forward / reverse will increase, thus resulting in no net change in position. There's not one reaction direction speeding up and one kind of slowing down. They stay constant in their increase of rate, and therefore, because both the rate of the forward and reverse will increase, the reaction simply reaches equilibrium faster. But no change in position. Okay, so that's kind of interesting how this external stress actually doesn't create any net change in equilibrium position. It does create a change in the overall rate of the reaction. Everything's moving faster. But if everything moves faster at the same magnitude, you still get your equilibrium position remaining constant nevertheless, okay? What about adding a catalyst? The same is true. that there would actually be no effect on equilibrium because, again, when you add a catalyst, okay, both the forward and the reverse reaction will increase, okay, because you're changing the mechanism, making it easier for more particles to effectively collide and produce your desired bond rearrangements. But since it's in both directions that the activation energy has been lowered, the pathway has been changed, making it easier, no actual change in equilibrium positioning toward reactant or toward product is actually favored in the end. So your equilibrium is just simply obtained faster by the reaction, but not changed. Now, what about a response to a change in volume? Well, for gaseous systems, i.e. gas reactions, okay, for gaseous systems or gas reactions, what we see is that a change in volume does shift the equilibrium. And what will happen is that what we see is that when we change our volume for gas involving reactions, a shift will occur. Okay. And how do we, a shift will occur. Oh my goodness. And how do we understand why the shift occurs before I even describe what the response will be? Well, you got to remember, according to, I believe it's Boyle's law, okay, Boyle's law, that, gosh, I hope I'm right. Boyle's law, or the isolation of two variables from the ideal gas law, pressure and volume, that if we decrease volume, we increase pressure. And if we increase volume, we decrease pressure. And that means for a gas system, pressure is indicative of concentration for that gas. So when we change volume for a gas system, we are changing pressure, which means we are also inherently changing the concentration of gas particles present. Okay. So what will happen? Well, let's look at the actual responses. If I am going to increase the volume in a gas-based reaction, I will decrease the pressure. Therefore, my reaction will shift to restore the pressure, to restore the initial loss of pressure, to restore initial loss in pressure by favoring the side with more moles, of gas. On the reverse, if I decrease my volume and therefore increase pressure, the reaction will shift to restore, or actually to alleviate, initial increase in pressure by favoring the side with less moles of gas. So let's look at the example below. Here we have an all gas reaction, and the system described by the equation below is compressed. So if I increase, compression, if I compress, that means my volume is going to decrease and my pressure is going to increase. In what direction will the reaction shift to restore? Okay, so what happens is, to restore this, we are going to want to, according to Le Chatelier's principle, and I'm going to say Le Chatelier's LCP. That's going to be my shorthand for Le Chatelier's principle. Okay, LCP. According to Le Chatelier's principle, to alleviate that additional pressure, initial pressure increase, what we will see is that the reaction will favor the side with less moles of gas. So on this side of the reaction, we have 2 moles of gas. 1 plus 1 equals 2. And on this side of the reaction, the product side, we have 1 mole of gas particles. Okay, that's the ratios, 2 versus 1. So what will happen is our reaction will shift toward product side that has less moles. That has less moles of gas particles. Okay, in order to alleviate stress of added pressure. Okay. And then it asks us, how will the number of each type of molecule and the concentration of each substance compare to those before the system was compressed? Well, what we would see is we would see an increase in product and a decrease in reactant, essentially, right? We would see that the reactant concentration would decrease and product concentration is now increased. All right. So for aqueous solutions, water as a solvent solutions, do we see that a change, okay, in volume will affect the rate of reaction, and particularly not just the rate of reaction, but create a shift in the equilibrium. All right. And what we would say is that if you are to change the volume, right, by adding water to change volume, okay? So another way of putting it is maybe by diluting. By diluting, okay, the solution, we see a decrease, okay, in overall solute concentration. Okay, so what will happen is if we were to dilute the solution, the reaction in an aqueous environment will, oh my goodness, these bells. The reaction will shift in a way to relieve the change in solute concentration. And this could be said vice versa, right? It's a little hard to make a solution have more molarity unless you just straight up add solute, which would then follow the standard understanding of added concentration. Okay. This is kind of just a unique take of like looking from a dilution perspective of aqueous solution, what would happen? Okay. Generally speaking, we see that the direction of the reaction with more moles, so forward or reverse, the direction of reaction with more moles of particles is more sensitive to changes in volume. Okay, is more sensitive to changes in volumes regarding their response. Let's look at this example problem here. So what we see is for iron and I kind of forget what that cyanide, it's not cyanide, but it's like thiocyanide ion when forming FeSN2 plus. What we see is that if we were to dilute this aqueous synthesis, reversible synthesis reaction, we would see that we would shift toward reactant because what we want is the side that has more moles, right? Reactant side has 2 moles of ion. Product side has 1 mole of ion, is more sensitive to the volume change. And what we're going to want to do is we're going to want to alleviate or restore that initial stress of greater volume, less solute concentration by adding in more solute through the reverse reaction being favored. Okay. Now, something to note is that for volume change and pressure change, we're still under the category of how does a reaction respond to change in volume. Whether you're a gas or an aqueous solution, whether you are a gas or an aqueous system, what you'll notice is that if the sum of the mole ratios is equal on both sides, so let's say reactant and product are 2 and 2, then volume change has no effect on equilibrium. Okay, so that's something just to keep in mind. Like I have 2A goes to 1B goes to B and then C. Okay, what we see then is that there's no effect because as you notice, we are dependent on, our responses are dependent on there being a difference in mole amount of particles on the respective reactant versus product side. So that is something to really remember, is that all of this discussion proves fraught if you do not have a different mole, sum total mole particle value on product versus reactant for both a gaseous and aqueous system. All right. So go ahead and try these next 2 problems on your own and pause me. All right, so hopefully you got the following is for the sample problem. If you were to decrease volume, what you see is first of all, you check if we have a different mole ratio. We have 3 moles of particles on the reactant and 2 moles of particle on the product. So you now know that this is even worth your time. And then you would say that with a decrease in volume, you increase pressure. So we want to alleviate that initial pressure. So we're going to shift toward products with less moles of particles. Okay. For the second one, you should again have checked that you have a difference in mole value. So you have 2 moles of particles over here and 1 mole of particle on the product side. So you know that again, a change in volume does have an effect. So now you look at the problem and you say, well, what would happen if we have diluted? So if we dilute, okay, if we dilute, we increase volume, means an increase in volume and a decrease in pressure, or another way of saying it is decrease in concentration, another way of putting it. And what we're going to do is we're going to shift to the side that has more, okay, more mole amount. So we're going to shift toward reactant. Shift toward reactant, producing more moles of ions. Okay, to help alleviate that dilution. So what about temperature? Temperature is another really important factor that could be a stress. And temperature is really simple. You always have to know if you're exo or endo. So you can't really answer this question unless you're given an indicator through the enthalpy value or some energy written as a product or reactant, whether you're exo or endo. But once you've identified whether you're exo or endo, you can kind of think of temperature now as a reactant or a product, depending on its placement. So if you're exothermic and you add heat or you raise the temperature, reaction shifts toward reactants. Okay, because if you're exothermic, you kind of think of, okay, heat some reaction, A goes to C plus heat. If you're exothermic and you add, right, you add more, you're going to have more product. So what are you going to do? You're going to try to use up your energy product by shifting back to the reactants. On the other hand, if you, okay, remove heat or you lower the temperature, what you'll see is reaction will shift toward products because now you are at a loss, okay, at a loss for heat. So what you're going to see is that the reaction is going to shift to restore, right? Restore that loss in heat. The opposite is true for an endothermic reaction, where you have heat as a reactant, and you, if you were to add heat, okay, you would see the reaction shift toward product because now it's like you have too much heat reactant. And so what you would see is your reaction would shift in such a way that it wants to use up that heat. And vice versa, if you were to remove heat, your reaction will shift toward reactant because it's like you're lacking in reactant. So you want to fill up that gap by favoring the reactant side. When we think about the exothermic versus endothermic direction, I believe I mentioned this in Unit 6 as well, but remember that the exothermic direction, the exothermic rate is always more favored. So the equilibrium position will generally always favor exothermic, the direction that is more exothermic, okay? Exothermic direction more favored, which of course affects the equilibrium position, right? Affecting equilibrium position. If in case you guys were like, I don't know why we need to talk about that, right? So go ahead and try out this sample problem and we're almost done. And then I'll do a quick summary and we'll be good. Okay, so for the sample problem, you should have, okay, realized that if the system is cooled, what we have is we have an endothermic reaction because of a positive enthalpy value. So if we cool the system, what we're going to see is if it's endothermic, it's like heat is a reactant. We're removing that heat by cooling. So we will see a shift toward reactants to replenish or restore the heat loss. Okay, to replenish or restore the heat loss. So here's a quick summary of the factors according to Le Chatelier's principle that affect the equilibrium position by creating one direction of reaction to increase and the other to slow down. Okay, and so what we see is external factors that affect equilibrium reaction rates are concentration shifts. Okay, and don't forget that a shift also affects yields. And two, temperature. So when we see temperature increase, okay, it's important to know that, oh, I think I put the notes in a funny way. When temperature increases, we have to first examine if it's exo versus endo and respond accordingly. But I do want to mention this little side note for a gaseous system, okay? I'm actually just going to leave that. Oh, well, for a gaseous system, what we're going to do is if we talk about temperature increase with a gaseous system in a closed container, we're going to ignore the effect on pressure to isolate the response, okay? So normally you would say to yourself, if we increase the temperature for a gas involving system, we would see an increase in pressure, which would make us want to favor the side with less moles. Here, we're going to ignore that initial fact and just focus on more temperature. Is it exo or endo? Okay. And then for pressure and volume, stress only occurs, or an equilibrium shift due to the stress of pressure and volume changes only occurs when we have unequal moles on reactant versus product side. And then as a kind of a little final caveat with gas systems in a closed container, if pressure is increased for a gas system in a closed container and theoretically a rigid container, we are going to do the same thing where we ignore any change in T. Okay, that might be associated in order to isolate the Le Chatelier principle response. Okay. So it's kind of like similar to the one above, these caveats. Overall, the reaction will respond to the stress being applied, which is what Le Chatelier's principle is all about. So if you do see a stress question, and there are so many equilibrium Le Chatelier problems, remember that we focus on the response, right? That is our focus, is on the response. And if there is a stress applied, unless it's one of these special caveats where you don't have change in moles from reactant to product, or you are a heterogeneous reaction, or you are some other sort of caveat, you will always see the reaction shift its equilibrium to restore and undo that initial stress. So good work, you guys. Sorry, this is so last minute. It's a little disorienting to have school be canceled, but I hope that you will come in tomorrow. We will go over Le Chatelier's principle, and you do have an AP problem tonight to do on Le Chatelier's principle, which will also clarify things for you as you actually just get into problems. Because right now it's a lot of conceptual right here. It's a lot of things to keep track of. Just start getting into the problems. Start just thinking about your little imagery of a balance, or if you like to image like physiologically yoga, trying to stand on balance, like create your own analogy and get into the problems. And I promise you, this will end up being a really actually lovely section because, yeah, it's just about responses. So good job, you guys. Have a great one. Bye.